video. Hello everyone, this is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar where we would like to show you a simulation of an airfoil. We call it Acoustic Benchmark. It's a CFD simulation of NACA 0012, where together with CFD, there are also simulated acoustic profiles and acoustic properties. And in this webinar, we would like to show you how to do that. We have created pretty universal workflow, which is capable of acoustic simulations based on CFD, and we would like to share it with you today. I hope everything is working well. The webinar is being recorded, and the recording will be available. We will publish it perhaps tomorrow on our YouTube channel, so feel free to find the recording there. In the webinar, there will be a couple of parts. In the first part, there will be general introduction. We will say just necessary general things. And in the second part, there will be expert on air, and the expert will explain a little bit more in detail what's going on, how to view, how to approach things. He will mention a couple of more details, and in the last part of the webinar, there will be a Q&A session dedicated to your questions and our answers, and we will be happy to answer all your questions. The most representative questions will be answered right away in the webinar, and the specific questions will be answered later via email, but you can be sure that all the questions will be answered, and we'll be happy to discuss with you, and we'll be happy if you get engaged and discuss with us, because we are also very curious about your opinion and how let's say what else we can do with this, because it's definitely very promising. Yes, so this is the introduction. I'm here with my colleague Radek Maca. Let's check him. Hello, Radek. Can you see us?
Hello, Luboš. Yeah, I can see you. I can hear you. Hello, Luboš. Hello to the audience. And yeah, I'm looking very forward to this webinar because it's more than 2 months since our last webinar. So
right.
I was getting sick about the webinar, so I'm looking forward to have it today.
Right, great. Thank you, Radek. Great to have you here. We are looking forward to your contribution. It's always very, very, very informative. And yeah, so yeah, I think we can go ahead. So now we will switch the cameras off, right? As
okay. Yes.
Typically want to do. And okay, so still I hope you can see my screen, and I will just make like 5 to 10 minutes of necessary introduction. So let's start. So I guess you know the company name is CFD Support. We are located in Prague, Czech Republic. We are 15 years in the market, doing a lot of things, mostly connected to CFD. But in general, it's much more. It's not only CFD, it's also FEA, FSI, optimization, and acoustics, which is today's webinar about. So yeah, our flagship product, the main service is definitely TCAE, which is simulation environment. It's pretty comprehensive because there are a lot of options and a lot of degrees of freedom and a lot of flexibility associated with it. TCAE consists of several modules. Those are software modules which can be used in a combination with your or whatever workflow, existing workflow. There can be created a new workflow. As mentioned, there's a lot of flexibility associated with TCAE. TCAE can be used just as a solver for CFD or FEA or anything else. It can be combined, used together with in-houses, another open source, with commercial codes. There is a lot of flexibility involved, and TCA is definitely extremely cost effective because there are no limitations of number of users, number of licenses. There are no limitations on job scores, hardware installations. So you can be sure that you will use your resources to the fullest for a very, I would say, acceptable amount. TCA is focused. It's focused mainly on rotating machinery and external aerodynamics. That's where TCA is best. It's generally not a general purpose code. It's not software for everything. It's great on specific cases, or not just specific cases, but it's focused on this turbo machinery and external aerodynamics. It's perfectly automated, and it's always up to the user. It's up to the user who decides how deep to go into the rabbit hole. So it can be used as a black box, or it can be used as a highly sophisticated code, simulation code for research, for example. So it's always up to the user how it's going to be used. So again, there's a lot of flexibility and cost effectiveness associated with it, and that's the main reason. Those are main reasons why it's so successful. We also do pretty a lot of benchmarks, so we always compare with the real physical measurements, we compare with the other solvers, we compare with all the physical data that are available to make sure that those virtual simulations are real, they're as real as possible. So we do a lot of benchmarks. Most of them, a lot of them are publicly available, and yeah, TCA can be run in various modes. It can be run remotely. It can be run on laptops, desktops, on cluster cloud, from home, from the office. It can be run natively in Windows and Linux. The workflow is the same everywhere, and gives a lot of freedom to its users. Really, a lot of freedom. It's based on open source. That's the real reason why it's associated with so huge amount of value, because a lot of has been developed in advance, and here at CFD Support we acquired the ability to put the things together, put all the functions, all the software pieces together, and to add the extra added value to it with the graphical interface, with smooth engineering, and with project management, etc., etc. We have aggregated more than 40 many years of development of this product of TCAE, and I hope it tells a lot that on top of all those open sources, we still have added more than 40 many years of focused development in an engineering team and team of developers here to make this. Yeah, so the latest release is 23.10, and we are already working on the new release. We have three main, I would say, three main strategies. We are focusing on the optimization, for sure. Optimization is great thing. It's paradigm shift. We have been talking about it many times. So definitely one of the priorities for the future for the research is the optimization. We are working on it constantly. The second one is completely new. It's based on machine learning. It's a new simulation, or it's a new software module which will help the users create his or her or their surrogate models. It's a really big thing. Again, paradigm shift, something different from the optimization, but they work together perfectly. Great thing, but this is not what I wanted to talk about today. So I will go ahead. The third big focus is the acoustics of the simulations of acoustics. So that's what's today's webinar about. So definitely acoustic simulations is something what we have developed a lot in the recent period of time. So we have improved significantly everything what was available so far. So I can tell you that the simulation module which takes care about the acoustics is called TCAA, and it's based on acoustics analogies. It's based on the library Acoustics. We have written it to be capable to take industrial cases. It's used as a post-processing. There's a special way how to store the acoustics data to rerun the acoustic simulation in anytime later. So nothing is forgotten. Everything is stored in the special data format. So from the CFD simulation, we can extract the acoustic properties of the flow and of the fluid flow. Yeah. TCAA became a smooth part of TCAE ecosystem. It has its GUI, graphical interface, and we are constantly working on new benchmarks to show the validity, to prove it works, and it gives really reliable results because it's simulation, and we can compare it with the measurement data for sure. So very important part of this acoustics analogies and simulations are benchmarking. So we constantly create new benchmarks to confirm and to increase the credibility of the simulations. In the past, we have tested the drone propeller benchmark. It has been released, and you can find it on our website. Today's webinar is about this NACA airfoil acoustic benchmark. Again, all the data are available. We are extremely transparent, and we are proud of that all the cases we are showing today, you can download them. They're transparent. You can read all the information about them, and you can rerun them anytime. So those results and simulations are perfectly repeatable, and again it's possible to prove their work and make all the tests and everything. So it's extremely transparent, and we'll be happy to guide you through the process if you like. So today's webinar is about the NACA airfoil. So it's a very significant case because it's, I would say, industrial applications are huge, and there are a lot of them. And for the future, we are working on another a few new benchmarks, which the most significant cases are axial fan optimization. We have a great benchmark for axial fan with the measurements and everything again. So it will be released later this year. And also one centrifugal fan CAA benchmark is available, and we have I would say agreement with those authors that we can publish the data. So at least two new benchmarks will be released on acoustics still this year, hopefully this year. At least one we will do this year for sure, because we have the results already. So you can look forward to new I would say proofs that the methodology is developing. There are new capabilities, new features, and definitely a lot of confirmation and validations with the real physical measurements. So that's what's on the way. And finally, I'm getting to today's topic. So it's NACA symmetrical profile 0012, perhaps the most widespread acoustic, airfoil profile. So it's well known. We have simulated it according to the article which has been published a couple of years ago. It's called Bank 3. So there's an article where all the details are discussed in the detail, and we have like rerun this simulation with our technology and our workflow to let's say test everything, and to show it how the workflow works. So we did. We have achieved pretty good results, and we would like to show you everything. Everything is very transparent. So yes, so this is my general introduction, and now I would like to hand over the presentation to my colleague Radek. So Radek, are you still there?
Yes, I'm still there and awake.
Absolutely, that's great. That's definitely great. So I would like to, yeah, we can see your screen. So the stage is yours.
Okay, thank you, Lubos. Thank you for your part. And now I will smoothly continue with the topic. And basically, I will present more details about the workflow. I will not be speaking about all the details about the models and so on, but I would like to show you the general workflow and how the acoustics is implemented and joined into the standard workflow. So as Lubos mentioned, the case is publicly available. If you go to our web pages and go to the case studies section, you will find on top this NACA 0012 benchmark, and you can click on it, and all the information can be found here. So first of all, there is a description of the workflow of the benchmark. Then it is summarized in a PDF report, and there is also the simulation report from the acoustic module, so you can go through it by yourself. And last but not least, you go through the information here. At the end, you can also download the case and, for example, ask for a trial license and try it by your own and get your own results on this benchmark. So I will take this PDF report and I will go through and I will mention all the, let's say, part of the workflow. So what is very nice that the workflow from the CFD point of view doesn't differ from any other CFD workflows. So the CFD simulation itself, including the meshing, is set with a standard approach. What I would like to mention maybe here, just quick, that what was the team of this benchmark. So we are working, three of us in CFD support company here, and with our colleague from the Vestas, with Matthew Gallot, who brings this benchmark, and using this one we are developing the more advanced workflow for more advanced topics. So about the interface, so the standard interface, everything is implemented in the TCE, so maybe it's good time to jump into the GUI. So because it's under heavy development, the full let's say full applicability and full all the features are now implemented in the upcoming version, which will be released soon or within a month or something like that. So I am using the developed version, and here I will load standard case. So I have prepared it here. Yeah, so here the TCE benchmark case. So it's the case you can download on our web pages and open it and run it by yourself. So first, the workflow consists of setting up nice and reliable CFD workflows. So you can't start with acoustics without the confidence in the CFD result that they are giving what you need. And then if you are really sure with the results, everything works fine, everything converts fine, the getting integral values are very close to what is expected. So then you can go for the acoustic analysis. So this is the compulsory steps to have perfect workflow for the meshing, for the CFD simulation, and then you can go for the acoustics. So as you can see, the workflow looks like a standard one. And if I go back to the presentation, so the first step is to create a mesh. So depends on the on the application. Like for example, for the propeller, we have a standard 3D domain where the impellers or propellers were put in. So here for the airfoil profiles simulation, where we really need to have a fine mesh and fine resolution, we can't, let's say, simulate a 3D full 3D propeller design or impeller design, which has several meters of a span. Here we have just a cutoff of the span where we can apply the periodicities or symmetry boundary condition depending on the application. And here to achieve the meshing and the automated meshing for the several types of airfoils, or it is also prepared for some kind of adding serrations for optimization of the acoustics on the airfoils. So we stick with the standard SnapX mesh tool, and for these purposes, because the domain is pretty large to get rid of the boundary effects, so the domain has to be large as in the standard external aerodynamics applications. But because of the span is very thin, like we can see it here, so we have just, for example, 10% or 5% span of the chord, so it's really thin region, and we would like to save a lot the cell size or overall count of the cells in the far field, so far from the design of the airfoil. So we developed this, let's say, methodology that we, using standard block mesh approach, we designed this red domain, this external domain with a standard hexahedral topology. So if I go here to the CFD geometry, surface with edges, so this is a standard topology of the or hexahedral structure mesh basically, and here we put the standard STL domain, and this domain will be meshed with the SnapX mesh. So if I go to the T mesh, to the components, so component 1 is the standard external mesh, and the component 2 is the mesh which will be meshed by the SnapX mesh using the STL geometries. So we have here several objects. So we have front and back side of the domain. We have the interface on which the standard AMI approach is applied, and then we have parts of the airfoil. So in this scenario, the pressure side and suction side are divided separately for the further specific post-processing, but it can be put as a single STL. So the workflow is still the same. And here, yeah, Luboš?
Okay, you can hear me. You can breathing. Okay, Radek, thank you for your sensitivity. And maybe at this point, we would like to like double check that we are talking about the red is the in these terms it's the external mesh, which is could be the same or all the time, and the green one it's just STL, right? It's just the surface, and yes, it will be meshed during the process, right? So what we are looking here at the green part, it's not the mesh, right? It's just the surface, and we wanted to enhance it, to show it, but it's just the surface which will be meshed, and we can say how fine it will the mesh will be. So it has not been set yet, or yeah. So that's not a mesh. Yeah, the mesh is much finer, and we have complete control over it. So we for example, as you can see here, we can say we will have like 15 inflation layers. What will be the refinement? What will be the how many levels, etc., etc. So we have all the options over the meshing. And what we are seeing here is not the real mesh. That's just the surface that surrounds the volume mesh. Okay, thanks.
Yeah, thank you, Bosch. And the resulting mesh then looks like this. So we can visualize it here in the CFD mesh item. And if we look on the final mesh, so then we have very fine, nice results mesh with a high inflation layer size, and this is the resulting mesh together with the external one, as Luboš mentioned, and this is joined together and used as a simulation domain on a simulation mesh. So I think we have summarized the mesh statistic here. So at the end with this particular variation of parameters, but you can play with the mesh refinement depending on the flow parameters and the targets of the simulation. And then here we have the standard or the mesh statistics about the sizing we have chosen, and as the output we have something like more than 3 million cells depending on the chord size, object size, etc., and what is needed to achieve. All right, so this was the strategy about the meshing. So basically I will not go into much detail. So this can be done, and for this workflow, if you would like to simulate the different airfoil topology, you can just replace the STLs of the airfoil, and then you can run the whole workflow again with the same setup. So for example, for the optimization loops where you will vary some new features on the airfoil, then you can vary very effectively just in the loop, and after this optimization loop is done, you can go just for the results, and no manual interaction is needed during the optimization loops. So this was the mesh, and for the CFD settings, the setup is almost the same like all the other problems and projects. Maybe if I go for some summary, so for this particular simulation, we go for the physical time of 1 second. The time step is chosen to reveal the frequencies up to 10 kilohertz, for example. The acoustic data samplings are done from the 0.5 seconds, so we would like to keep the solver to evolve to a converge condition, like everything is converged on the blade, and then we are evolving just the periodical movement, what is happening on the blade. The sampling is done on the airfoil, so the surface of the airfoil is the sampling surface to have the data for the acoustics. Particularly, we are sampling the pressure and the densities, but in general, you can also choose some external shape on which you sample data in the free stream. But for this particular case, the sampling on the surface is I think is the most straightforward method. For the simulation, we go for the first the steady state simulation is done just to initialize the flow, and then the transient simulation is applied with a K-omega SST DES model. Here are the flow parameters of the simulation. So we have free stream velocity of 53 meters per second and angle of attack of 6 degrees. So depending on the CPU and depending on the mesh resolution, but for example, for this case, we have the simulation takes something like 600 cores, which means on the PC with, let's say, 30 cores, you can have the results within a day. All right, so this was about the simulation, CFD simulation. When we go back to the GUI, so the setup is a standard one. So we tell the times for the simulation. We always suggest to use the steady state initialization, because then transient converge much faster, because it has some initial shape which is close to the real condition near the blade, and then it takes less physical time to evolve to some periodical movement and to some converged flow pattern on the airfoil. Fluid properties and all the other parameters are set in the standard way. The turbulence, you choose this one. So okay, omega SST DS is for transient simulation, and when we initialize with the steady, then it automatically switch to standard K omega SST model for the steady state calculation. For the solver, you can choose any number of processors you need. Delta T, the time step depends on what you would like to achieve, what frequencies you would like to resolve, and the frequency of the sampling of the data, of course. And what is new here is inside the runtime evaluated quantities, you have the section of the write acoustic data. So if you would like to go for acoustics, you need to enable this option. And here you define when you would like to start sampling the data, because you can imagine how many data it will take, because we are sampling every 5 to 10 to minus 5 seconds the data on the surface. So for each phase on the surface, we are sampling the pressure fluctuation at every time step and the density fluctuation. So to save some data, we can start sampling from some point. Typically here we are using half a second, and from this point all the data are sampling, and then this data are used for acoustic analogy evaluation. You have many options. For example, if from CFD point of view you need to have some finer time stepping, but from the acoustic point of view you don't need to have the frequency of the sampling at every time step, so you can go for the every second time step and so on. So you can apply the write interval here. The format, so it's from binary, because then the acoustic analogy can read it and use it. Acoustic surface type, so here we directly sampling on the surface, but for some other applications you can use some reference surface around your objects, for example, and for this purpose you can use the external STL, which will be then used as the sampling surface, but here we are using the patches. And basically from this simulation, from this information, the data are sampling, and this is all you need to set for the acoustic analogy evaluation in the next step when the simulation is done. The other parts like the forces, for example, to evaluate the lift and drag coefficients, are set in the standard way as usual, like the probes. So to follow some fluctuation at a specific point within the domain can be also set. All right, so here I think it's all only for the inlet and outlet boundary condition, because we have such a domain which is simple to create, and it's so for this reason we have basically two inlets from the X main from this side and this side, so from the X main and Y main in this case, because we are simulating positive angle of attack. So we set free stream velocities and we set the particle value of the free stream pressure and the inlet velocity vector, and basically this is set for all the inlet outlet boundaries. So it is easy to change the angle of attack, or this can be also connected with the T-opt and managed, for example, different angle of attacks within a single click, like within the loop. We can simulate different angle of attacks if needed. For the wall, standard boundary conditions. So because the mesh is very fine and the boundary layers are resolved, so we can go for the lower Reynolds functions. And as we will see from the report, we target to the y plus around 1 interface condition. So between the external and internal mesh, we set the standard MI approach because we have non-conformal mesh, but far from the object, so we do not influence the results. So this domain is just for the keeping the boundaries far from the object, and to resolve the flow fully, we use the internal mesh. All right, so this was about the CFD simulation, and here we have some nice animation from the CFD simulation, which are then used for the acoustic analogies. So if I go here, so this is what we also can. This is what we get from the simulation. We sample every time step, so then we can see really the nice flow patterns, what is happening, and so on. So to check the flow patterns from our simulation. All right, so all the standard CFD simulation can be or parameters can be evaluated and post-processed in the standard way. And what is specific for our benchmark, so you can evaluate the for example the CP, so the values on the airfoil, typical for the airfoil, like these pressure coefficients. So we have developed some scripts which can manage both span-wise and time averaging data to really have a specific data for the given transient window and for the given span, which can be then compared to the experimental data or some analytical data to validate that your CFD results are correct. All right, so the same you can done for the surface pressure evaluation. This is a little bit connected to the acoustics, so you can evaluate the pressure fluctuation. From this pressure fluctuation or density and pressure fluctuation, you can evaluate the power spectral density, which is also commonly measured for some experiments, and compare these data also with the experimental data. But this is part of the acoustic analogy. So if we go to the last module, TCAA, we can go through the menus and see what can be said. So again, it's pretty straightforward. And again, I need to emphasize that to start with the acoustic analysis, you need to have a perfect CFD simulation to obtain a good and accurate results. So what we have here, the acoustic source data are taken directly from the simulation, or if you have some previous simulation where the acoustic data were stored, you can choose the external data and go for the particular sampled data and evaluate just the acoustics, which is, for example, nice if you when you tailor the acoustics for the specific project. So you need to somehow play with the parameters of the acoustic itself, mainly with some kind of filters and so on. So you can have a one CFD simulation and then play just with the acoustic evaluation. The custom time range, so here you can set, okay, I have some sample data, but I need to use just part of them, so you can tell which time frame will be used for acoustic analogy. Then you can set the observers, so the acoustic analogy take the sampled data on the surface, and from this source, this will create the sources for the acoustics, for the acoustic waves, and they are simulated to propagate to the observer position. So you set the observer position when you would like to have the acoustic analogy, basically you would like to have the acoustic data, basically this power spectral density or sound pressure level. So you put the coordinates of the observer, And here we implemented, let's say, 3 versions. So single observer position, or if you have more specific observer positions, you can import them also as a CSV file, or you can have a circular distribution, so where you can automatically set the distribution of the observers, which is specifically used to have some kind of nice polar plots, which I will show you later. There are also the possibility to add virtual observers, because we have some kind of single observer for a single span, so you can put some kind of the copy to extrapolate the data to some, or scale the data to a specific span, for example, span of 1 meters. Maybe I will be also speaking about this later. So these are the observers, and when we can go back to this presentation. So here there are some examples of evaluated power spectral density from the specific point where we compare with the measured data. Here, for example, we also compared the acoustics data with the particle fluctuation of the pressure at the given point, and from that we made a Fourier transform to validate the methodology. So here we have validated several different points and different probes. And from the signal processing, so we are now coming to the real signal processing. So these were the inputs, and for the signal processing setup, we need to just set the speed of the sound and the reference sound pressure level, which correspond to the 0 decibels. And here in the signal processing, you can apply some high and low frequency filters to get rid of some kind of fluctuation and oscillation, which can be caused from the simulation itself or from the numerics itself also. So you can clean the data, move to the zero level, and some advanced processing for the Fourier transform. So these steps are summarized here on this slide. So this raw signal we get is centered to the origin, and the Butterworth filters are applied to get rid of some high and low frequencies. And then the Welch method is used to transfer the signal to frequency spectrum, and with a Hahn window, which is specific treatment of the signal before the Fourier transform is applied. So it divides the signal into this given number of windows. So I think the rule of thumb is to use these 3 windows, and this will also get rid of some kind of artificial data inside the signal. And then, yeah, from this from the signal in frequency domain, the sound pressure level and power spectral density is evaluated, and yeah, everything is preset here. So we have already mentioned this setup, and the main output of the acoustic data or acoustic analogy simulation are the sound pressure level. So here you can see the signal in the frequency domain, and the red and the green lines are the transformation of the signal into the 3rd octave band or the octave band, which is typical. So this 3rd octave band is typically used for final outputs of the signal of the acoustic measurement. So as you can imagine, the acoustic is really the acoustic depends on really accurate and trustable CFD results. So you need to have really fine mesh, refined mesh, and all the parameters are important. So here we have, for example, the comparison of the data for which we got very nice results, and we even go for the more refinement, mainly on the wall, to achieve, let's say, even more accurate data. And if we compare to the measurement, so here is a typical comparison to the measurement by the benchmark, which we have taken as a data to compare with, is yeah, maybe I'm going into too much detail. So what we get is the output for the given span we have chosen, but typically the data are measured for 1 meter span or are scaled to the 1 meter span to be comparable with different approaches. So if we take our signal from the TCA and scale it to the 1 meter span, which were presented in the study, then we've got such a nice result. So basically, we are comparing the red of the output of the TCAA with the third octave band of the benchmark. So this is the comparison, and right. So this is the comparison, and for this data, as I shown you, if you create these polar plots, so these circular observers, you can then have these plots. So where you have the decibels for each observer at given frequency site. So for each frequencies you have chosen, so you have put it here in the post-processing in the report. Which we have somewhere here, but maybe I have late. Yeah. Okay, let's go back. So these are the polar plots, and basically I'm at the end on my site. So maybe Lubos will add some information. So just to conclude my part, the CFD part and the meshing part are always the same. So it's a standard approach, and to activate the TCA module, you need to adhere the acoustic data evaluation, which then in the acoustic module, you can take them, set the typical observers in which you would like to hear the sound, and as the output, maybe it's good to go to the report. You will have all the information about the acoustics. So for each observer, you will see the unfiltered, so the raw signal which coming from the data. These are the filtered signal, and then you can go for the power spectral density and sound pressure level for each observer, and you can also add the data to compare. So this is the data for the scaled one, but this is for the standard span. So, and go for the other frequency like the probes. So you can input the probes, so specific point on the evaluation surface, and then you can follow the density, the power spectral density, and or the pressure itself, the pressure fluctuation to compare with, and then you have the polar plots for each frequency defined, and you can follow the values here. Okay, so maybe it's time to go back to Lubos to add more information, maybe, or to go for the discussion.
Okay. Yes, Radek, thank you very much for your part. It was great. It was balanced. So thank you. And okay, I will take back the presentation. Okay. So I guess you will see my screen soon. And yeah, so to conclude these first two parts, the workflow has been created, and we have shown it on this NACA test case. And of course, it's universally, or it can be used on many other industrial applications. So the beauty of this case is that all the data is available. Everything has been explored. Everything is known. The case can be downloaded, and it can be further investigated. It can be researched again and again and again all the way through, and it can be definitely rerun. And the beauty of this case is we have the data and we have the measurements, and we can compare them. And it has been done in the case study, and all the presentations, PDF, everything is available. So just to conclude this, and I think we can move to the last part of this webinar, which is the Q&A session. So I would like to ask the audience to ask your questions, and we will do our best to answer them and discuss. So feel free to ask, and we'll do our best to answer your questions. Yep. So let me see what we have here. Yes. So okay. So of course, those some questions are typically very specific, so we will answer them later via email. Alexandros is asking if we can explain the background of the lip acoustics, and yeah. So in the meantime, Alexandros has left the webinar, but anyway, I will just briefly say that that the lip acoustics is a set of libraries for OpenFOAM. Of course, I guess you know that OpenFOAM is the core CFD of the CFD part of TCAE software, and lip acoustics is a set of libraries and function objects that allow to evaluate the CFD parts. Especially it's based on acoustics analogy, so the sources of special sources of the sound are transformed, and and evaluated for the acoustics. I think a lot of it's the far field method. I think if you Google lip acoustics, you can find all the information, because it's open source, so you can find everything about it. Yeah, so it's this. Yeah, and yeah. Radek, I have a question. What's the typical, because very typical question is about the simulation time. So can we elaborate a little bit about that?
Yeah. I think we have slightly mentioned it. So for this case, which has more than 3 million cells overall, the simulation took 600 core hours. Yeah, so depending on the machine you have. So if you have, for example, 30 cores, then, or 32 cores for the machine we have, for example, in our company, so then you can have the results within a day. But as you know, it depends strongly on the mesh refinement, size of the object, time stepping, and so on. But for example, the results we got for the benchmark, we got, let's say, within a day on the
okay. So we can say that
machine.
Typically it takes about 1 day on a good PC.
On a good PC, on this specific low span airfoil design. Yes.
Sure. It's yeah. Okay. So it's this, and what else? I can see any representative question here at the moment. So Radek, I think we can conclude the webinar.
Yeah, sure.
So we have a couple of questions we will answer via email, because they're too specific to individual cases. Yeah. So okay. So yeah. So we are going to conclude the webinar. So yeah, here are a couple of those who already share our visions with us. Anyone is welcome to join us on our journey. We believe we have a lot to offer. The software is getting better and better all the time, and we believe it offers a huge amount of added value, and we're ready to prove it. So yeah, this will be it. Radek, any last word?
Yeah, thank you for watching. And just to mention, we concept this meeting or this webinar as a general information about the workflow we have. And for those who would like to discuss more details about that, then we are open to have a discussion via email or later when you contact us. So we will answer all your questions, and we will be glad to discuss with you your goals or your view of this project or of this benchmark.
Yes,
So do not
absolutely.
hesitate to contact us.
Yes. No, thank you. Yes, absolutely. That's the point. This is just the kickoff, right? It's the invitation for a discussion for evaluate the things and testing things and do some real engineering here. Thank you. Okay, this will be it. So we'll leave you with that. Feel free to let us know. Get in touch anytime. We'll be happy to assist, and we will leave you with that. So thank you and bye bye for now.
Bye bye.
Bye bye.